right, great. Okay, great, everyone. Great to see you. And this is Chuchu. I'm very happy to be here like virtually. I'm sorry I cannot be there in person today, but I will be at RSS in a few days and hope to see some of you there in the last 2 days. So today I would like to share some of the work on code as symbolic planner via guided code text generation. And this is going to be a joint presentation with my student Yongchao. So, in my group, especially with Yongchao and a couple of other students and postdocs, we are looking at planning problems, particularly planning problems with constraints. They are NP hard problems. And over the past decades, people have developed a lot of the different domain-specific tools for different research areas like the web search or the logistic domain or robotics, and sometimes even like planning for driving your EV around the country or planning a trip to travel around. So we, as many of us have been working on developing these domain-specific tools, we wonder whether can foundation models like LLMs can, fundamentally solve these problems without asking to use the tools? If not, then the second question is there a way to incorporate these tools into the large language models to help LLM as an agent to solve problems, but users do not have to use how to learn how to use these domain-specific tools. So in a very short period of time today, I would like to introduce a few work. So I will spend most of my time in my first half talking about how we can use LLMs plus rigorous solvers to make very complex plans in the travel planning domain. And I will just briefly mention that how this can be easily extended to almost a plan for anything, including problems in robotics and in supply chain and logistics without providing in-context example. After that, I will hand it over to Yongchao to talk about enabling his recent work about enabling LLM to automatically choose between generating a code to query the tool or use the text-based reasoning to solve various problems. So as the first half is specifically asking LLM to use tools, but we also know that in some tasks, LLM is also good at solving these tasks using just text-based reasoning. Now, can we do not just like ask LLM to use certain type of tools, but instead automatically decide how to proceed? So our motivation start with this planning problem, travel planning. I'm pretty sure a lot of you have done it recently, either to plan your travel to RSS, or if you're local, I'm sure you have been traveling somewhere in a recent couple of months. And we all know that planning a travel is a very complex and tedious process, especially when we have multiple levels of constraints. If it is for a vacation, we may have to think about the time window, the budget. If it is for a business-related trip, there are also different levels of considerations or constraints that our organizations will pose, and we all have to consider those in planning for our travels. And for the last couple of years, I think around 2 years, people have been trying to ask this question. Can we ask LLM to solve complex travel plans? And can we, for example, some of you probably have already noticed certain travel planning websites have already incorporated the large language models to help you make a travel plan. And researchers from a couple of places last year, they created a benchmark for travel planning. What they have done is basically to create a large data set of different destinations, transportation methods, hotels, restaurants, etc., to like a fixed data set and collect more than 1,000 different queries of like travel planning problems that people normally would ask and ask the following few questions. First, can LLMs directly generate a plan that will fit all of our requirements? As you can see in the red box here, this paper was published more than a year ago, and their conclusion at that time was GPT-4, which was the state of the art at that time, was not able to handle travel planning problems, and the success rate was extremely low, less than 1%. And we also tested on the most recent GPT-4o and o1. They have some improvement, but even if we give all the information needed to make this travel plan, it's still the success rate is pretty low in the sense that they may give us a plan, but the plan will not fit in all the needs that we have raised, like the timing and the budget, etc. Now, our initial thought is we have been, as researchers, especially researchers who work on planning for robotics, we have been developing tools and algorithms to solve these planning problems, especially planning problems as combinatorial optimization problems. And now, travel planning is actually a very special case here, and it's not like more complicated than the robotic planning problem that we've been dealing with. So how about we ask LLM instead of asking LLM to generate a travel plan, we ask LLM to write code that can query a solver, for example, something called SMT solver. Maybe some of you have heard about it. If you have not, that's fine. It's a special type of combinatorial optimization solver that is complete and sound. And I will talk about why this completeness and soundness is important here. But if we are able to write the right prompt, ask the LLM to translate from this English description of a travel plan to the code that can be consumed by the SMT solver. SMT solver will be able to give us the concrete plan. If we do that, the success rate is already a huge boost from the original result. So using GPT-4, you remember the result was like less than 1%, but still using GPT-4, the success rate is jumped to be more than 93%, both on the validation data set, which has about 200 queries, and on the test data set, this is around 90 for GPT-4. I'm sure if we replace it with a more up-to-date OpenAI model, it will get even more improved. And this is a plug and play model in the sense like we can just replace this model with any model. And this work was done more than a year ago, and at that time we saw that if we use the right solver, it pretty much could already solve the problem. Now, travel planning may not be that of a time-consuming and tedious task for our day-to-day life. So here we're showing with some just a little bit of more work, we can now ask LLM as agent to open your browser, go to your favorite travel planning websites or your like just a flight data set, etc., to collect this information. So all of this is a screenshot of what this framework can do online. It is opening the Expedia, but you can definitely change the website to be something that you prefer. And probably we'll skip most of this to show you like once you collect all the information from web, it can know the real time information about flight price or other type of transportation, or hotels, restaurants, etc., and compile everything, writing the code by itself, query the solver, and give us a plan that is as detailed as like which flight you can take, which restaurant, which attraction you can go. Now, as I said, this solver itself is more than just give us a plan. So this solver we are using is complete in the sense like when there's no plan exist, we actually can identify what we call the unsatisfiability core, meaning which part of my query make this plan infeasible. For example, in this particular case, there's no direct flight between the two cities, while in the user query, the user want to take a nonstop flight. So we can narrow down to the core reason for a plan to be infeasible, and then collect some information about other type of transportation, other destinations that could also have the same type of attractions that this visitor want to go, etc., and make a suggestion. The user may say yes, and then the code will be automatically updated to find a new plan, or the user may say no. In that case, we can just make another suggestion based on our understanding of the user preferences. For example, our suggestion could be about removing the nonstop flight information, and user may take it or may say no. Then we can make another suggestion to change the destination, or it might take a few iterations like raise the budget or change the destination. When the user says no, we can ask it whether they want to visit a different types of church than the one that this user originally described. And after a few iterations, it may get resolved. In this case, in our online demo, when we decrease the budget, this original plan become infeasible, and now we can basically start the same process. In terms of the performance, If we allow 10 rounds of iterations, this is tested on different type of users where the users could always say yes, or the users does not want to change the budget or change the destination city, etc. We have a decent success rate here among between like 70% to 90%, especially here, as you can see, if the user always agree with our suggestions, and then within certain number of iterations, we can always be able to fix the plan. So that is basically the first type of the work. With just one more minute, I want to tell you like a little bit of extension. Our original travel planning was a pretty big success, boosting the success rate of LLM for planning, travel planning from 1% to more than 90%. But still, this is a slightly domain specific. Remember, our goal is to have a general planner, but now this is focusing on the travel planning problem. So we have to provide this task-specific in-context example. Is there a way to eliminate this and develop a general purpose framework? And we have a iClear work that followed on this previous travel planning work that take the idea that many planning problems, the core of it lies on our optimization problem. So searching for the optimal solution is basically the same as searching for the best plan, and the constraints is the same as a preconditions and effect on the decisions in our robot planning problem. So I have a supply chain problem, basically looking at how we are collecting the coffee beans, sending those to the roasters, and then eventually to the retailers. And there are all these descriptions are in English, but we can extract the core variables constraints as a combinatorial optimization problem, send it to solver. Now the solver will be able to solve cross-domain generate tasks. So let me skip this architecture very quickly. But as a result, now we can see that this with this new enhancement, the planner can really do general purpose planning across domains. On the top is the planning with multiple levels of constraints in logistics and supply chain domain. And the bottom here is planning with planning for multiple steps that has different types of robotics problems. And overall, with the GPT-4o and Cloud 3.5, we have also a pretty good success rate, jumping from very low, especially in the supply chain and logistic domain, from less than 1% if we directly query the LLMs to about 80. Now, remember, this is not asking you to provide any in-context example, just directly describe your planning problem. Now, with that, I would like to take it, ask Yongchao to take it over to show you maybe we don't even have to ask the LLM to choose a specific solver or require to use a solver, but automatically decide whether it should use a solver or use a different tool or just use the text-based reasoning.
Okay, so next I would like to talk about how to use code as symbolic planner as another mode. So currently we have like the two typical types of methods to use LM as a planner. And the first type is like use LM as a direct planner, like the typical work, secant code as policies. So, but the challenge here is that when using LM as a direct planner, there is no symbolic computing for the decision making and the task and motion planning. And the second mode here is use LM plus an actual planner. For example, LM plus P or auto temp or travel planner. In this case, the limitation is that the generalization across different tasks will be limited, because for each specific task, we need to choose one specific symbolic solver, like PDDL or temporal logic or SMT. So here we are thinking like whether there is a third mode, and third mode is like LM directly generates code as a symbolic planner. So in this case, LM will generate a code, but this code is not to like connecting different modulars, but to directly generate the code as an optimizer or planner. So, but in this case, the good thing is that this code will inherently carry out the symbolic computing. And the second is that there will be a very enough generalizability, because LMs, they can first reasoning about the task with textual reasoning, and also they can generate different versions of code. So I will start with one very simple example in the LM reasoning. And here, these two tasks they are very famous these days. I mean, you just ask GPT-4o like 9.11 and 9.9, which is bigger, and then the answer is wrong. And also you ask the like in the word strawberry, how many R's in this word and their positions, the answer is also wrong. But actually, what we do is that if we just add one extra prompt here, like use code to solve this task, then you'll see the answer will be correct, because in this case, the ChatGPT, they will generate the code and then execute the code. So in this case, for these two tasks, generating code will be a much easier way to solve this task. But the problem here is, how can LLMs choose between a code and text without hints? I mean, during the common usage, the users will now pre-specify like you need to use code or text to solve this task. So how do the current methods they try to handle this problem? And I think the one very typical method is from OpenAI. And what they do is that they fine-tune the model so the model can inherently learn when I need to call the code interpreter or not. So for example, when we ask a question, the ChatGPT will like first generate the textual reasoning to analyze this problem, and then generate the code, and then execute the code and do the further reasoning based on the execution results. However, in our recent IPL work, we try to analyze whether this code interpreter is good enough, and our finding is that there are many limitations. So here is a very simple example. So just like two numbers multiplying together, so when we use like GPT-4o, the ChatGPT version, and it's two-digit number multiplying two-digit number, and then the answer is correct. However, when it's like a many-digit number versus many-digit number, the answer is also correct, because you can see the blue tag here. This means the LM generates code to and execute it to answer the question. But the problem arises is like in the median hard one. I mean, 4-digit versus 4-digit. In this case, the answer is wrong, because in this case, the LM will directly answer with the textual reasoning, and then the textual reasoning is wrong. So we do a more quantitative analysis. So you can see in this figure from the on the x-axis from the left to right, the complexity of this task will grow. And you'll see when the task is too simple, the answer will always be correct, because in this case, the LM will generate the text as an answer in all the times, and then that answer is correct. And when the complexity is high, the answer will also be 100% correct, because in this case, the LM will generate a code all the time. And the problem arises in the middle. In the middle, you can see the red part. I mean, in this case, it shows the LM generated a text to answer the question, but the answer is wrong. So are there any better methods to get the LM code text generation? So our framework is like this. So we're fine-tuning a smaller model, like 8 billion model, called the code LM, to assist the generation of the man LM, the task LM. So when input a question, the code LM will first review this question and then generate the guidance, like utilize your programming expertise to address this task. And then the task LM will generate the answer based on the prompt guidance from the code steel. And once the code steel feels the current answer is wrong, or the current code is wrong, then it will generate the guidance again, generate more complex code. Then in this case, the task LM will optimize their answer. And once the code still fails, then it will return answer. So that's our general framework here. And so to realize it, we first gather and redevelop 37 symbolic tasks with scripts to automatically synthesize testing samples. And all these 37 tasks, they involve the symbolic components. And then in the first stage, we just fine-tune the model with supervised fine-tuning with automatically synthesized data while rejection sampling in the multi-rounds. And what we found one problem is that for the multi-round SFT, there will be an issue of the gradient cancellation. For example, when you input one question, the first trajectory can be like user test first, and then the answer is wrong, so it switch into the code, and the answer is correct. And the second trajectory can be directly use a code, and then it's correct. So in this case, these two trajectories, they are both correct, but they will cancel each other in the first round. In the first round, because I mean their choices are opposite to each other. So what we do is that we just do the data augmentation in the final 2 rounds to avoid this issue. And in the second stage, we do the directly DPO, direct preference optimization, to further optimize this model. And we can see the performance. So here, when augmenting GPT-4o with code steal, you'll see the performance will be even better than the pure reasoning model without the code interpreter, like DeepSeek R1 or OpenAI O1, because these models, while they are very good at textual reasoning, they are not good at the code interpreter. So we can also apply this into the robot planning. So here you can see there are some typical tasks involving highly complex symbolic reasoning. So in this case, we can directly query the LM to generate the code as a planner or solver. So that's the whole about our talk. Like first, one note is that integrating symbolic computing with LMs is important. And secondly, is like we think coding maybe is a very good mode, because coding is very natural to LMs, and also it's generalizable and symbolic. And also, like with too strong generalization, we can training some smaller models to guide the decision of larger models. So that's all. I'm happy to take any questions.
All right, thanks so much, Chuchu and Yongchao, for teaching us how to use foundation model, large language model with the solver and as symbolic planner. In the interest of time, we just take one question.
Yeah, when you generate code, sometimes it has syntax errors. So how do you deal with this?
Oh, yeah. A very good question. So you can see our guidance is multi-round. So in this case, for example, in one round, if the code has errors, the execution error will be returned back to LM. So in the next round, for example, the code still, and we are like, maybe you need to generate better code considering these errors. Yeah. So during this multi-round way, many syntax errors can be avoided. But still, sometimes there will be some errors that the current LMs can't handle. Then in this case, sometimes LM will directly switch into directly textual reasoning to solve this problem without coding. Yeah.
Okay, let's give another round of applause to